Hey, welcome. Have you ever stopped to think about how a simple idea, an algorithm, gets turned into a physical piece of silicon that basically runs our entire world? Well, today, that's the exact journey we're going on, from those abstract lines of code to the real, custom-built hardware that makes all our tech tick. Let's dive right in. This phrase right here, it just nails it. It's not just about science, it's an art. Think about that. It's the creative challenge of taking a digital concept and figuring out the absolute perfect physical structure, the architecture, to run it as efficiently as possible. That's the core idea we're going to be exploring.
Okay, so first up, let's talk about the processors you probably don't even think about. We are literally surrounded by these tiny, specialized brains in almost every gadget we own, and each one is a master of its own little universe.
And yeah, there's a technical term for this, an embedded processor. Now, unlike the super powerful chip in your laptop that's designed to do pretty much anything, an embedded processor is a specialist. It's built for one specific job, and its success isn't measured in raw speed, but in how tiny, how cheap, and how power efficient it can be.
Now, this is where it gets really interesting because it's all about trade-offs. The processor in your laptop, it's a high-performance beast, ready for anything you throw at it, but man, does it drink power. The embedded processor in your microwave, though, it does one thing perfectly, runs the controls, while sipping power and costing next to nothing to make. It's really the difference between a Swiss Army knife and a surgeon's scalpel. And this isn't some abstract stuff. These chips are everywhere. You've got the Snapdragon in your phone. That's a system on a chip, or SoC, which is basically a whole computer packed onto one tiny piece of silicon. But you also have things like digital signal processors, or DSPs, that are masters of audio. And then you have ASICs, application-specific integrated circuits. These are built for one and only one task, like mining cryptocurrency or accelerating AI. These are the unsung heroes of our digital lives.
Okay, but what happens when the job changes? What if you need a specialized circuit, but you also need it to be, well, adaptable? This brings us to a really revolutionary idea, a chip that isn't set in stone.
This is the big question, right? Building a totally custom chip, an ASIC, is incredibly expensive, and it's permanent. If you get it wrong, or if your needs suddenly change, you're stuck. You have to start all over. But what if there was another way? What if you could have the raw speed of hardware, but with the flexibility of software?
Well, there is a solution. It's called an FPGA, which stands for Field-Programmable Gate Array. The most important part of that name is field programmable. It means that you, the designer, can program and, more importantly, reprogram the chip's internal wiring out in the field long after it has left the factory.
So how does this magic actually work? Honestly, the best way to think about an FPGA is like a giant, super-powered box of digital Legos. You have this huge collection of basic building blocks, and you can connect them in any way you want to build pretty much any digital circuit you can dream up. So let's take a look at the actual bricks. The most fundamental piece, that one single Lego brick in our massive kit, is called a CLB, or a configurable logic block. It's just a tiny, really versatile little unit of logic that you can tell what to do.
And each one of these little blocks is surprisingly capable. It can handle basic decision-making, it can remember what happened in the last step, and it can even do a little bit of simple math. On its own, it's not much, but its real power is in the numbers.
Okay, so here's the kicker. An FPGA doesn't just have a few of these CLBs. It has thousands, sometimes millions of them, and they're all sitting in this sea of programmable wires, or interconnects. When you write code for an FPGA, you're essentially creating a blueprint that tells it exactly how to connect all these simple little blocks to create one giant, complex, and highly specialized circuit. What we're talking about here is a total game changer in how we think about hardware. We're moving away from the idea of fixed, rigid circuits to something that's more like digital clay. Hardware that can be molded and, just as importantly, remolded to perfectly fit whatever task you need it for at that moment. So let's just put it all together. The whole journey looks something like this. You start with your idea, your algorithm. Then you map it directly onto the FPGA's architecture, creating a custom piece of hardware. And here's the most powerful part. When your algorithm gets better or your needs change, you don't throw the chip away, you just reprogram the one you already have. It's incredible.
And that leaves us with this one big, kind of mind-bending question. In a world where AI models are evolving every few months, where new communication standards are constantly popping up, is the old-school, fixed, single-purpose chip becoming a liability? Will the future of computing belong not to the strongest chip, but to the most adaptable one?